Good evening, folks. My name is Marc Razze from JPL's Office of Communications and Education, and it is my absolute pleasure to be your host for tonight's edition of the Von Karman series. Tonight, we'll be talking about an upcoming project called SunRISE, which, as you may have guessed, will study our sun. But before we get to that, please say hello to our co-host tonight, Universe Public Engagement Specialist, Chelsea Gohd. Hey, Chelsea, how you doing?
Hey, Mark, I'm doing great. And hello to everyone. As a reminder, this is a conversation, and you, the audience, are a big part of that. So whether you're watching on YouTube, X, Facebook Live, or LinkedIn, please don't hesitate to ask questions in the chat box, and our social media team will bring in as many of those questions as we can during our talk tonight. If you do not see the chat box on your screen, reload your page and it should pop up right there.
Thanks, Chels. So, the SunRISE mission to study the sun is not one spacecraft, but rather an array of 6 smaller satellites, with the intent to help us understand how the sun works and how it generates such intense solar storms, like the coronal mass ejection you see in this video. With that information, we may be able to better predict space weather, which can then help us protect both spacecraft and Earth assets from damage caused by these solar temper tantrums. To tell us more about the mission, our guest tonight is Mr. Jim Lux, the SunRISE Mission Project Manager. So during his 25 years at JPL, Jim has delivered numerous products, including deep space transponders for the Artemis 1 mission CubeSats. He was the principal investigator for NASA's Space Communications and Navigation Testbed, and he has won 2 NASA Exceptional Achievement Medals. And that's all after he had an award-winning career in physical special effects for film and television. Hey, Jim, thank you so much for joining us tonight. We're thrilled to have you.
Good to be here tonight.
So let's start off kind of big picture and tell us a bit more about the mission goals and like how those were determined.
Okay, if we could have the first image up. SunRISE is going to look at the sun, radio emissions that are related to those coronal mass ejections you just saw, those big bursts of chunks of itself. Our principal investigator from University of Michigan says it's like the entirety of Lake Michigan being launched into space from the sun. Maybe so for us, it's kind of like all of Los Angeles and the Griffith Park and everything else getting launched into the sun. And so that goes hurtling out, and there are charged particles in that mass ejection, and where the charged particles accelerate, they give off radio waves. So what we're going to do is we're going to fly an observatory in space that can image where the radio waves are coming from, and that tells us where they're being accelerated, and that tells us more about what's going on inside the sun and where things are coming from. So one of the interesting things is that as these bursts move out from the sun, the radio waves they give off drop in frequency. And so if you see on the picture there's, it starts out at 10 megahertz, which is sort of in the middle of the shortwave band, and it slowly decreases as the burst moves out into the heliosphere. And these phenomenon last 3 or 4 hours. So it's not something that happens flash and it's gone. The movie you saw is greatly speeded up. Okay, so why did the scientists want to do this? We got the next picture. There it is. So it turns out where you gather multiple heliophysicists in a room, you'll have multiple hypotheses about what's going on inside the CME. And so what SunRISE is going to do is, because we know they give off these radio waves, it's going to tell us where relative to the CME it comes from. Does it come from the front where that light bulb, like the top of the light bulb where number 1 is, or does it come from the side as it expands out, or does it come from the middle, or maybe somewhere totally different? In any case, SunRISE will give the scientists the information needed to be able to distinguish among all these hypotheses and therefore figure out more about what's going on inside the sun.
Okay. So how do they work, and how come like 6 spacecraft as opposed to, I don't know, any other number?
Well, six spacecraft is 1 more than the minimum number we need to make our measurement. So the way we do this is what's a process called interferometry. And what we do is we compare the signals that are received at each of the spacecraft in turn, what time they arrive at. By looking at the difference in the time of arrival, we know where the emissions are coming from. And so with 6 spacecraft, we can have them arranged in space in a way that lets us know where relative to the sun it's coming from.
Okay. Now, is this one of those types of missions where we kind of have to be in space for that, or is that more advantageous?
Yes, very much so, because the signals we're looking at, these shortwave broadcasting signals, what we call the decahectometric, that's the wavelength, hundreds to tens of meters, are sufficiently low that the ionosphere on Earth blocks them. So, you've probably heard about, shortwave radio. You can receive a station that's from another continent because it bounces off the ionosphere. But when the ionosphere is a mirror like that, it's also a mirror for the signals coming in, and so we can't see them. So you pretty much have to be in space to receive these signals, and that's where we're going to be, up above geosynchronous.
Okay. All right. So help me understand, how do we create the images with this interferometry?
Okay, so if you look at number 3 picture, so interferometry has been around a while. What it does is that if your source is bright, and for these things, the radios, it's bright, you don't actually need to have a complete mirror reflector that surrounds everything to collect all the light. The signals are strong. What you really need to do is you need to have it spread out. And so radio astronomers have had these arrays of telescopes, and they combine the signals. And that's just what SunRISE is going to do, except we've got 6 of them in space as opposed to a couple dozen out in the desert in New Mexico. That's the very large array at the National Radio Astronomy Observatory in the picture there. So what's interesting, this whole thing about interferometry is kind of interesting. If you go to the next picture, there's sort of a local connection here, is that up on Mount Wilson, you've probably seen, those of you who are local have seen the domes up there, or maybe you've been up there to see it. And this is a picture of the Hooker telescope, the famous telescope that's up there. And a guy named Albert Michelson, who kind of invented the interferometer for light, built one that mounted on the end of the telescope. And with that, he was actually able to measure the diameter of the star Betelgeuse. So we won't say that any more times. And, just to give a sense of scale here, that interferometer is about 6 meters long. If you took one of our space vehicles with all of its antennas and you plonked it on the middle of there, it would be about the same size as that beam across the top.
Okay. All right. So how are we launching these little guys into space?
Okay, so we're going to do what's called a ride share. This is pretty common now for small spacecraft. What it is that somebody else is going somewhere where we want to go, and we kind of hitch a ride with them. In this case, it's the United States Space Force has a launch on a kind of rocket called the Vulcan, and they have something that's going to geosynchronous. And what we're doing is we're sort of mounted underneath the primary payload. They'll launch up, they'll drop off the primary, and then they'll go a little bit higher, 300 kilometers, and then drop us off. And then it turns out there's other payloads that one of them is going to go off towards the moon, and I don't know what the third one's going to do. And so we'll get up there. Right now, the official date is the fall of 2024, but this is a space flight, and you never know when you're actually going to launch. Other than I know it won't be before the fall of 2024. It'll probably be later. Yeah. Okay.
All right.
Let's see. We could probably go for the next little video here. One of the interesting things about this is that, so there you can see a picture of a couple of engineers working on. So those sort of gold-colored boxes you see on the bench there, those are our spacecraft all neatly folded up, just like they're going to be put into space. And then when they're in space, they'll unfold. And so this is what we call the interferometer level performance test, which is a fancy name. But it's designed to, we actually operated all 6 of those space vehicles from the operations center here at JPL, and we commanded them for 4 weeks. We operated them just like it would be in real life, and we would send commands up to them. They would record signals generated by those boxes on top there that simulate the solar signals and the GPS signals, and then we record it, then we'd bring it down, we process it, and make sure it all worked together as a actual constellation.
Oh, that's really neat. I love that you can simulate that whole process. So in our previous conversations, when we were talking about the history of this mission, it sounded like it was pretty colorful. Would you be so kind as to like dive into some of how this got started?
Sure. One thing that it's interesting when we talk to people at the open house and things like that is it takes a long time to get a mission like this started. So way back in 2015, here we are, 10 years later. Some folks in our mission design and navigation section came up with an idea that we could put a number of satellites into orbit and they would stay reasonably close to each other and stable. So this is a real problem. Is you put up a spacecraft and gravity and the sun's radiation pressure tend to make it fall out of its orbit, but there are some orbits that you can actually make stick reasonably close together. So they actually figured out how to do this in Earth orbit, out near the moon, and at some of the Lagrangian points, and that we'd be able to keep them there without using a lot of propellant, because you have to keep nudging them to be in the right place, and you can only carry a certain amount. Those space vehicles aren't very big. So what happened is that around 2016, NASA put out an announcement of opportunity. That's what the call for proposals is. We started responding. So we had a concept for the mission. We wrote up a proposal and submitted it back, and then you wait and you wait and you wait, and in 2017 they said, great, you've done step one, you can now try another more complete proposal. We think the science is great, you're going to make a great measurement, we think you know how you're going to do it, but we want more details. So we wrote another proposal, and you have to do this all within a cost cap, in the sense of that NASA's not just writing a blank check. They say, no, you have to do it for $55 million, which sounds like a whole bunch, but you got to build a bunch of space. You have to design things, you have to build a bunch of spacecraft, you have to operate them for a year, you have to get them into space, and there's a lot of these little pieces and you got to kind of keep some reserves because things will come up and you're going to have to spend some money on that. So we got our concept study report in for phase 2. NASA comes out and spends a day grilling us on all the questions at the site visit, which is a novel and interesting experience and kind of grueling. And then after that, you wait, and then they came back and said, okay, great, but we have these few extra questions. This is kind of like the Columbo, just one more thing. So we spent another year answering those questions, and then finally in 2020, in June, we actually started. So it's kind of funny. They had this meeting called Authorization to Proceed, or KDPB. We were probably the first mission at NASA to have an entirely online authorization to proceed, because it was in the middle of COVID. COVID had just started. If you remember, from here at JPL, we all went home in March, and here we were in April going to this thing, and we had this approval meeting with all the NASA dignitaries and the administrator, and then we got approved, and we started actually working in June, and then here we are, 3 years later, all of our little spacecraft built and in storage, waiting to launch.
Bravo and congratulations.
Yeah,
that's quite a road. So that's great. Before we move on then to part 2 of our talk, which is going to be more about like the operations of these things, let's check in with Chelsea and see if there's any questions you can kind of field at this point. How's it going out there, Chelsea?
It's going great. We're getting a ton of really wonderful questions for you, Jim. Cool. Christy over on LinkedIn asked, how is SunRISE different from other missions monitoring the sun?
Well, we're the first one that's going to be looking at it in this particular part of the spectrum. Now, as you've seen the videos of the coronal mass ejections, those are from what are called coronagraphs, and they're typically visible light or UV or maybe infrared. This is looking at it in these low radio waves, which we've never observed from Earth, where we can't observe from Earth. And so that's one difference. The other thing is that we are observing essentially continuously for a year. We're just continuously recording. We get all the data down. And so we don't have to worry about trying to detect that something occurred and then quickly record it.
Definitely. So we've got a few more. I'll just throw one more your way for now, and then we can come back to these questions in a bit. But we have Shagaf on YouTube asking, what type of instruments specifically or technology will SunRISE use? And they're also curious if the SunRISE technology and these small sats are being manufactured at NASA's Jet Propulsion Lab.
Well, a combination of the two for as regards to manufacturing. But if you look at it, what we call the payload, that's the actual measuring part of our space vehicle, is a combination of a GPS receiver and a receiver for the DH signals from 100 kilohertz to 25 megahertz. And we designed and built that here at JPL. And we built 6 of them, plus we have a couple of engineering models, and we have another unit that we use for testing. We shipped those to Space Dynamics Lab in Logan, Utah. They're part of Utah State University, and they build a lot of big and small spacecraft for these kinds of things. They've been in space business as long as JPL has. So what they did is they built the space vehicles. In other words, they machined the chassis, they went out and bought the propulsion system and the attitude control system, and they built the flight computer, and they assemble it all together, slide our payload in, connect everything up, and then they do all of the environmental tests and thermal vacuum and vibration testing and all that thing. And then at the end, they're going to be stored there until we call for them to be brought out of storage.
Fantastic. Well, thank you for taking a couple questions. I'm sure we'll get back into them later, but for now, I'll throw it back to you, Marc.
Thank you, Chelsea. Thanks, folks, for the questions. And yeah, we'll have time for some more at the end of all of this. So now we want to kind of transition into operations. Jim, what's it like operating like 6 of these spacecraft?
An ordeal. Once you show image 6, and this are part of the challenge here. Okay, so this is kind of a artist conception that shows you, okay, there's our 6 spacecraft. Now they're actually moving, but you can see that they record and then they downlink to the Deep Space Network, and that happens once a week. So what happens is these things have to be self-maintaining for a week, and then we get 5 hours to talk to them essentially on the weekend, although that might change. And so we have to design the whole process so that they can operate themselves. And in fact, we really have to be able to have them be self-operating for 2 weeks, because what happens if there's a power outage or DSN has a problem or something like that? We want to be able to accommodate it. Or, Deep Space Network, they're the ones that are talking to Chandrayaan-3 right now. And so, there might be some other emergency that requires Deep Space Network to do their thing. So we always have to do that. So.
Wow. Okay. I can see where that can get complicated once or twice. Every 1 or 2 weeks. Yeah. So then what happens if there is some kind of problem on the spacecraft?
Okay,
how do they handle that?
Yeah. So that's actually what we call fault protection. And so the spacecraft itself is designed to look for problems. So there's what we call a watchdog timer that makes sure that the things are still happening when they should be. And if it looks like it got stuck, it'll automatically reset it. And or it'll go into what's called safe mode. Now, in our case, safe mode is science mode, because what does a spacecraft do in safe mode? Well, it points itself, solar panels, towards the sun, gets itself in a stable configuration. Well, that's what we do for normal science operations. So for us, safe mode's not much different. But again, we have this whole self-protection thing that happens. So hopefully, it reboots itself, comes back alive, and keeps on recording. And then once we talk to it the next week, we downlink all this telemetry, and we'll be able to figure out what in the world is going on, because what we'll see is a gap, right? Here's 6 spacecraft, we're getting all this data, and there's this little gap in there, and then there'll hopefully be telemetry that tells us what to do, and maybe we need to do something, or maybe it just happened.
Yeah. We know historically speaking, fault protection software has saved the day on more than a handful of occasions, right?
Oh yes. Look at Voyager last week.
Yeah. Yeah, right.
Yeah.
So if you haven't heard that story, folks, read that. Voyager, we recently lost touch with the Voyager for a little while. Got her back, though. We're good. But so what's it like then working kind of within that mission operations team? That's got to be kind of a fun environment.
It is. It is. There's a team of about half a dozen people who are doing the work. And now, what's interesting is that so they're only talking to the spacecraft on 2 days a week, but there's a lot of stuff for them to do in between. Remember, they get all the information down, then they have to process it, make sure it gets shuffled off to the science pipeline, make sure the spacecraft are healthy, and then figure out what the instructions are for next week or the following week, just in case there's no gap. So what happens is they have a operations center here at JPL, and it's not a huge office, and there's a bunch of screens in there, and you'll have 2 or 3 people who are monitoring what's going on with respect to the communications to the spacecraft. Are the files coming down? Are the files going up? And then there's sort of a background task of the navigators get data, once a week of where we are, and they're making sure that we don't run into ourselves. They're also working with Goddard to make sure that, because they're the ones who will warn us if there's something that might be on a collision course with us, and maybe we can move out of the way.
How close do these things actually fly?
So we want them to be about 10 miles apart at the most. So, maybe more like 6 miles average, but remember, 6 of them. We don't want them any closer than half a kilometer. What's that? 3/8 of a mile. Because we don't know precisely where they're going to go during the week. I mean, we have really good predictions. We actually know after post-processing where they are within a meter, which is pretty impressive. In other words, they're gonna fly for a week, we'll get the data down, and we'll know where they were every second with an accuracy of a meter, because that's what we need to make the science measurement. But we don't know if there's going to be some sort of bump in the atmosphere, in the interplanetary atmosphere, or some sort of pressure thing, or it's going to push them. And so we want to make sure they're staying away from each other.
Yeah, I imagine it's got to be pretty challenging trying to fly a tiny fleet of tiny spacecraft.
Right.
So they're able to maintain that formation. That's amazing to me. Do these things have like little propulsion systems on them?
They do. They have a little tiny propulsion system. Fit in your hands. It's about 4 by 8 inches, and maybe a couple inches thick, and it has a little tiny tank of a refrigerant in it. Non-toxic. It's like Freon, but not actually Freon. That's a trade name. Okay. And there's little tiny valves in it that squirt little bits of the propellant out to kind of nudge the spacecraft one way or the other. And there's 6 little nozzles on the bottom, and so they're pointed different directions. And so by squirting gas out the different nozzles, they can make it turn a little bit or move a little bit. I mean, when you talk about propulsion for satellites, you're typically talking about what they call the delta V. What's the total velocity change I can make? So for ours, over the entire mission, that's 4 meters a second, which is not a lot. That means that we can go this way, we can go one direction for a little bit, and then we can turn around and come back, but not a whole lot of that. And so it really is sort of a gentle. Imagine you're squirting a spray can, but smaller. That's pushing you around.
Wow, that's not a lot. You'd mentioned earlier though we use GPS to somehow maintain those formations. Can you talk a little bit more about like how that whole thing works?
Yeah. So if you look at the next image here, so one of the interesting things about SunRISE is that we're actually in an orbit that's way above the GPS orbit. The GPS orbit's about 20,000 kilometers high, and we're at 40,000, big round numbers. So, and if you think about it, GPS is all about navigating on Earth. So all of the GPS satellites have their antennas pointed at the Earth's surface. So it turns out that the satellites we're looking at are the ones on the other side of the Earth. And you can see the picture there is, the ones that are closest to our little spacecraft there are actually pointing the wrong way GPS-wise. So we're actually looking at the ones on the far side looking back. So we're about 3 times as far away from the GPS satellites as you are on Earth. But even with that, we can get good tracking. Like I say, we can, we track to a meter, and we know what time it is to about a billionth of a second, 1 nanosecond,
Oh, wow.
and which is actually pretty amazing. I mean, I've been doing these kinds of things, specifically that kind of thing, for quite a while, and yeah, the fact that you can actually build something like that that's going to go into space and it's going to go do it for a year and a half is pretty amazing.
Yeah, this is so neat. I can't wait to like watch this happen and then actually, start seeing what the data looks like when this comes back. This is going to be
what's coming back down. Yes.
Yeah, it's going to be so cool. So that all being said, then I think it's probably time to pop into the Q&A thing and see what's going on. So Chelsea, if you'd be so kind, how's it going out there?
It's going great. We've got a bunch of other questions. I'll start diving into them if you're ready, Jim.
I'm ready.
All right.
I could talk about SunRISE all day long and all night long.
Well, you're in the right place then. Perfect. We've got Sean Berry over on YouTube asking, what is the data going to be used for once collected? Are we trying to predict space weather more accurately using this in the future?
Yes, we are. So the raw data that comes down gets eventually turned into images, and you'll imagine a bright spot in the sky, an image with a bright spot on where the radio emissions are coming from. And so while that in and of itself doesn't let you predict things, what it does do is it tells the scientists how CMEs work. And CMEs are a big problem. When all those particles come bursting out of the sun, depending on how the magnetic fields line up, they can hit the Earth. And when they come and hit the Earth, some things are good. They make aurora. But some things are bad. They can cause electrical transients in power lines. And if you're a satellite, those particles hitting your satellite are not good for you. You can cause errors like the ones we were talking about earlier. And then if you're an astronaut, then you're taking more radiation dose. So the idea is that by understanding what's going on inside the sun, using the data from SunRISE, is we can predict by looking at the sun today what the sun's going to do tomorrow or the next day or after that. Right now, we don't have really good prediction. I mean, we know sunspots come and go on a roughly 11-year cycle. We know a lot about what the magnetic fields are doing, but remember, we're looking at the surface of the sun. We don't get to see what's going on. So this will give us something that looks at something that burps out and maybe tells us a little bit about what's going on inside the sun. And then the big long-term thing, well, the sun's a star like all the other stars. So, if we're going to study and understand how stars work, then let's look at the one closest to us.
Makes sense. So jumping into another question, thank you so much, Jim. We have Jankoji8 on YouTube asking if coronal mass ejections are directly related to the solar wind.
In the sense that they generate particles that become part of the solar wind. The sun's always streaming particles out, and so that's the solar wind. But what happens in the coronal mass ejection is you're getting a big bubble of them all coming out at once. And what's important to know is that the solar wind streams out from the sun, but it doesn't follow a straight line. It follows the magnetic field. So it's kind of, if you looked at it kind of from the top, I guess, you would see it follows kind of these curved lines. And that's one of the things that SunRISE is going to help do, is that there are other things that cause charged particles to come out of the sun, like solar flares. And by SunRISE, we'll be able to track those. And we'll know if those magnetic field lines are smooth or if they're kind of wiggly. And that in itself tells us more.
Definitely. Moving on, we have Ritwick on LinkedIn asking how this fleet of spacecraft will stay in orbit.
Well, it'll stay in orbit because there's nothing bringing it down from orbit. This is kind of the cool thing. We're up high enough. I launched a couple of CubeSats a few years ago, and one of them, the last one, finally fell out of the sky in November because of air drag. Right, if you're up at about 500 kilometers, or if you're down where the space station is, air drag keeps bringing us. You have to keep pushing the space station back up. We're up high enough that we're out of all the atmosphere. In fact, that's one of the reasons we're up where we are. And so we stay up there just because we're in a stable orbit around the Earth, and gravity keeps us going in our circular orbit. And a million years from now, SunRISE will still be in orbit. Probably won't be working. I don't expect to be working ops, but yeah, it'll stay up forever.
Well, that does lead me right into the next question, which is from Omar on LinkedIn, who was wondering if these satellites are sustainably designed for demise in Earth's atmosphere after the mission is complete, but it seems like they are not.
No, we do have the orbital disposal requirement, and we kind of get there in a clever way. When you're up that high, you can dispose of yourself into what's called the geo graveyard. So all those people have big spacecraft up in geosynchronous, they can just boost them up into geo graveyard, which starts at about 200 kilometers above geosynchronous. And so we're at 300 kilometers above geosynchronous. So we're already in the graveyard from the get-go. And so we are launching to the graveyard, and in the graveyard we will stay. Yeah.
And just to clear up a little bit of confusion from a couple of questions I'm seeing, the geo graveyard is in Earth's orbit, not orbit around the sun. Can you confirm for our audience?
Correct. Right. It's not. We're not gonna. Yeah, we're not gonna go into that. That's around the Earth. It just sits up there. Yeah.
Launching to the graveyard. I love that. So moving on, I have Greg on Facebook. Who's asking if SunRISE will wait for the solar maximum to launch.
Well, the solar maximum is kind of a fuzzy thing. It's kind of coming up real soon. We would love to launch at the solar maximum, or remember, we're going to operate for a year, and it turns out that CMEs are perhaps a little more common on the tail end of the solar maximum. But really, our launch is determined more by when our ride leaves. And so when the bus leaves the bus station, we've got to be on it. Right now, Solar Max is 2024, 2025. We'll be launching in 2024, 2025, so that's perfect. One of the things we had to do in the proposal phase is show that even if we launched at solar minimum 6-7 years from now, we could still do our mission. In other words, that we wouldn't see as many CMEs, but we'd still see them. And in the worst case, you see about one a month. But we hope, our fondest hope is that by launching close to Solar Max or CME Max, that we'll actually see half a dozen or more CMEs in the first few months of the mission. And we'll say, great, now if something goes wrong, we've got all our data, we're ready to go.
Sounds good. So we have a question from Nathaniel on LinkedIn, who's wondering who will have access to the data generated from this mission.
Everybody. There's nothing special about it or confidential about it. In fact, NASA requires that it be available to the public within 60 or 90 days after having come to the Earth. So what it is that we process it and then we move it all to what's called the Solar Physics Data Facility, the SPDF, and it's available to the public there, and anybody who wants it can download it. There'll be files out there that explain what the format is. So there'll be both the raw data that we collect, all that GPS data and the raw signals, and then the pairs of interferometry, and then the actual images. Plus there'll probably be images superimposed on coronagraph images for what they call context images. So yeah, everybody gets it.
I love that. That's a great answer.
It's what NASA does.
Okay. It's true, but it's great to be reminded that the data coming from these missions is for everybody.
Right.
Definitely. So I've got a question. It's also from Genkoji8 on YouTube. I know we've heard them referred to as SmallSats. Are these small satellites technically CubeSats? Is there a difference?
Yes, they are CubeSats. Ours are what are called 6U, because that the CubeSat is, for those, that's 10 by 10 by 10 centimeters, which, by the way, is the size of the plastic box that Beanie Babies came in. And so ours is 6, so it's 10 by 20 by 30 centimeters. So it's actually a little bit bigger. It's determined by how much you can stuff into the box that dispenses us. But yes, these are CubeSats. But generally what we've been doing is we've been moving to terminology of SmallSats, because as you start to get bigger than 6U and you get to the 12Us and 20Us, it starts to be, well, is it really useful to start talking about these little 1-liter chunks, or is it really just, it's something less than 50 kilos or 100 kilos? It's small. It's not a Mars rover or a Cassini. And so SmallSat just seems to be a better, more generic term without constraining you to the CubeSat model.
Definitely. All right, I've just got a couple more I'll throw your way, Jim. We've got Ryder on Facebook asking, why would you launch into a graveyard orbit? And how do you not hit other satellites?
Well, we launch into graveyard orbit so we don't have to move there later. Remember I was telling you about, we had 4 meters per second of delta V. To return to Earth, in other words, to go back down the atmosphere, is thousands of meters per second delta V. So it's essentially, we don't have even remotely enough propellant to do that. So that's why we're in graveyard, is because we don't have to dispose of ourselves. All we have to do is just make sure we won't explode by dumping all of our batteries and power and dumping all the propellant, and then we just sit there. And then what was the second part of it? Was the question was,
how do you not hit other satellites?
Oh, how do we not hit other satellites?
Yeah.
Space is big. You know, if you go and look at, there are some statistics out there, you know, how many satellites are at what altitudes. And if you're in LEO, there's just like dozens of satellites. So what happens is everybody tracks all these satellites. The U.S. Space Force tracks them. There are private companies that track them. People who operate them track themselves. So out of the 10, 20,000 things out there, everybody knows what the orbits are. And then they, multiple times a day, they go and they look and say, hey, is spacecraft 1 going to collide with spacecraft 2? Or is spacecraft 2 going to collide with spacecraft 5? And they, if you're going to get within a certain distance of each other, you get what's called a conjunction data message. Because you may not collide, you may just get close. And then it's up to you to decide what to do. Now, if you have a propulsion-less satellite in low Earth orbit, all you can do is watch, right? You can't move. Although there are some things you can do. Is you can turn your solar panels so they're either, because we got air drag down there, you can slow down a little bit or you can speed up a little bit. But for us, if we see that there's going to be somebody that might collide with us, odds are the other party also has some propulsion, and we can mutually agree on a way to move ourselves so we won't collide. You know, some of the satellites now actually do that by themselves. Starlink, for instance, they have computers on board that look and they see what else is coming, and they can automatically maneuver themselves out of the way. Because, you know, if you have thousands of satellites, you got to have something like that. Yeah.
You've only got 6.
Yeah, we only got 6, and we're in a pretty empty part of the sky. You go and look at the statistics, and, you know, there's like, I think the average distance between objects is thousands of kilometers. So it really is a giant, big sky. I mean, one advantage is, you know, the farther you get out, the bigger that space is. And so everybody's clumped in the geosynchronous belt, but we're not there. So we're somewhere else.
All right. Well, I've got one more for you, Jim. And I wish we could get to everybody. It's just a timing thing. But last but not least, we've got Stephen on LinkedIn asking if there are any recorded events or forecasts of any space weather breaking through our atmosphere. Well,
there's lots of space weather events in our atmosphere. Whenever we have an aurora, that's space weather. There was actually a large CME just before JPL Open House a few months ago, and there were auroras seen all over the United States. There's even sometimes aurora seen in Los Angeles, which is really unusual. So yeah, there are a lot of cases where space weather affects the Earth. You'll also see space weather effects, for instance, shortwave radio blackouts. You know, if you're used to doing shortwave radio and you're, you know, listening to Voice of America in Europe, or something like that, then all of a sudden you won't be able to hear it because the ionosphere is blocked because of the space weather.
Wonderful. Thanks so much, Jim.
No problem.
Chelsea, folks out there, thank you so much for all those questions. I wish we had time for more. Like Jim said, we could probably do this all day if we had the time. But
oh yeah,
Jim, before we wrap it up, do you have any like last words for our audience or advice for any of the viewers?
Well, this has been extremely fun watching the project come from the beginning, and we're getting close now. We're in storage and can't wait for it to launch. But this is just opening up a whole new window. I mean, we've never observed the universe at these frequencies before. So we're looking at the sun today, but maybe in 10 years we'll build another bigger version of this that can actually look at stars that are close to us, or look for aurora on extrasolar planets and things like that. So there's a whole, it is a totally new spectrum that we've not looked at before, which is really kind of cool.
Very, very cool. So we'll have to revisit this topic once you're out there and operating. I think we absolutely have to come back and pay this a visit. Yeah.
Yeah,
very
I think
cool.
So.
Definitely. Well, folks, that really is all about the time we have tonight. So I'd like to thank Jim, Chelsea, the social media and production teams behind the scenes. You folks are amazing. And of course, all of you viewers for watching this, submitting your questions, being a part of this. Again, this is your space program. So we are glad you participate in it, and we encourage you to continue to do so. So please be sure to return next month when we'll be talking about the upcoming solar eclipses. That's going to be a good one, folks. So until then, take care, stay curious, and have a great night.